try to summarize a little bit, right? Why do we want to go from RNNs to transformers, right? It's not like you're completely giving away RNNs. Something I didn't say clearly, and now I want to say it clearly. I want to start with the summary, right? So if you talk about RNNs and transformers, right? RNNs, especially like LSTMs, overcoming the vanishing gradient problem, they work reasonably well for long sequences, right? But you know, pay attention that first of all, it expects an ordered sequences of inputs because their architecture is utilizing that order directly, right? And then also keep in mind that we have this, you know, long short-term memory or GRUs recurrent. So we have this recurrency. We always have this sequential computation, right? The last cell will give input to the current cell, and I'm gonna use part of the last cell's memory and use some of the new cell's input and combine them together somehow to get the new cell's new state, right? This subsequent hidden state can only be computed after the previous one are done. So this is probably not a problem to you, but this is a problem for computers, right? That means you have layers or like GRUs or LSTMs that are sequentially connected, and there's no way that you can calculate when you do the backpropagation. There's no way that you can parallelize it, right? You have to forward propagation from first to the last, and the backward propagation from the last to the first. There's no way that you can break the sequential. But think about it. This is not the problem for transformers at all, right? So I'll jump into that. One of the best benefit is transformers using the self-attention rather than the sequential LSTM or GRUs. All these alignment, attention scores, and this can be done in parallel because we are just using X times W, right? That's all we do. And it's also good at long sequences, and each attention calculation looks at all the inputs. They can operate over unordered sets or ordered sequences with positional encodings. But in the meantime, this self-attention, this requires a lot of memory. There's a lot of alignment because you're aligning each to each. There's alignment matrix, there's attention matrix, and then they need to be calculated and stored for each single self-attention head. Remember, you usually have like 8 heads, and then you have the sequentially, this sequentially stacked layers, like 6 or 12 layers. So that's requiring a lot of memory, but we also know that GPUs are getting better and better, so that may or may not be a problem. Okay. But so since now we are done talking about transformers and self-attention, right? And what I talked about the self-attention and this multi-head and all this positional encoding were in the Vaswani 2017 paper. Attention is all you need. Okay. I think now it's time to talk about transformers, right? And so now let's look at the same examples like before, but now remember what we had was encoder decoder using CNNs or RNNs, right? And we had attention mechanism on top of it. We didn't use self-attention back then. We definitely didn't use transformers that utilize the self-attention layers. So if we were to do the same task, image captioning, using transformers now, what do we do? Again, imagine that we have this input here, and the output is going to be here. And we're going to have encoder on the left and decoder on the right. In fact, the first choice of the encoder is already given, which is a CNN, because early on we learned that CNNs are very good at accurately and efficiently extracting the image features, right? So that's what we do. Okay, let's start with this one. And we have the XIJs featurized or encoded into ZIJs by CNN, right? And then now for the and then we're gonna additionally add a transformer encoder here from zij's, right? So now notice that transformer does not care about the position actually, okay? The position is not in the architecture. It's not in the calculation x times w, those kind of things. Where is the position? Position is in the additional thing you put here, like the positional encoding. So on top of the CNN does not care about the position because it's already using the kernel that considers the positions. But here, in the case of transformers, you probably need to combine each z00 with some positional encoding, right? In this case, you probably need to do what? You need to do both horizontal and vertical positioning probably. Because essentially for transformer, it just regard the input as a sequence of, or a set of inputs. So you see that it's like Z00, Z01, Z02, it's like a vector, right? So it's something like, almost like revisiting MLP from the very beginning that, the order does not really matter until you introduce positional encoding, right? But of course we know that this is not a, MLP plus version, okay? So, but still it utilizes the fully connected layers a lot, right? Okay, so then the output is this sequence, right? Let's call it C. And then I could use this as input to the decoder, which is now replaced by a transformer as well, okay? And again, remember, I'm gonna have Y, and this is like the hidden state, H0, H1, H2 that I gave before, right? In the meantime, I also give Y0, Y1, Y2, like the start person wearing hat, the corresponding output should be person wearing hat end. So this is my golden standard ground truth label that we want to generate. Then we can compare the actually predict Y1 and the ground truth and then calculate the loss over all words and add them together, right? So you see that here I use transformers and I use it from the output of the CNN, and then its output essentially is, so now we split from here. On the left we have the encoder, on the right we have the decoder. The decoder is replaced by transformer, and the encoder is basically starting with the CNN, and we added a subsequent transformer, okay? Right? Any questions so far? All right, so my question is the following. Do we need the CNN? Do we have to use CNN? Can we do everything with transformers alone? What do you mean? I mean, I could embed here directly. So instead of Z00, I use X00, X01, and so on directly. Can I do that? You don't see a reason to object to it.
Yeah, except memory or...
Well, I'm not asking for more memory. I'm just removing the CNN. And here I use not Z00, but X00, X01 directly from the image pixel. Can I? Of course, plus positional encoding. Sounds possible, right? So before giving you the answer, I'm gonna talk about a little bit about the encoder-decoder block, right? Here I just show you as a block, but as we talked about, they are actually using, they are stacking these n blocks together, n layers together, right? N equal to 6. And the dimension of the query is 512, okay? And then we have multi-head as well. So we actually have multiple heads. So this is 8 of them, okay, multiple heads. So you could, do everything with attention alone, okay? But there's a little more in the Vaswani paper that we need to pay attention to before we conclude that we can just use self-attention everywhere for what we need, right? So we're going to talk about a few problems and how we fix them. Some of the fixes were actually already introduced before, okay? But now you can look at them differently. So the first problem is there are no element-wise nonlinearities. Remember, I have x times w, right? So there's no element-wise nonlinearities. So the self-attention is simply performing a re-averaging of the value vectors, right? So if I want to introduce nonlinearities, right? What should we do? So one possible way is that after these n layers of self-attentions, right? After each output of attention, so I add a feed-forward layer, which is MLP, right? And then which could be like W and then followed by activation function. This gives me the nonlinearity that I need potentially for the additional expressiveness, okay? So this is one thing, the nonlinearity that you can easily fix it, right? It's kind of easy to say than done, and there are a few more tricks. One of the three is already introduced before, the scaled dot product attention. But there are two more tricks that you haven't learned about, and let's talk about it. The first trick is the residual connections. Okay, it's a very powerful. It seems very simple, but it's very powerful. Okay. Somehow I'm missing the I don't know what is happening, but this image is missing some elements. So maybe your PDF looks good, but somehow when these PowerPoints goes from one computer to another, it doesn't show. It happened before. So let me see. So the first thing is that you want to add the residual connections. It's like a jump, okay, from the earlier layers to later. So it's like from the past to the future, okay? So I know that we usually have layers after layer, right? In this case, self-attention layers after layer. And they are sequential, but it's possible that you are using the output of the previous, right? But then you are adding the additional. So in other words, the input to the else layer, let's call it x sub l, is not only the output of the previous layer, f of x sub l minus 1, but also an additional input, which is x sub l minus 1, which was, you see that, right? So if you have, where's my pen? Nothing works. So imagine that this is x sub l. I pass it through a layer, then the output is going to be x